So, this class I will discuss about the design of footing under inclined and eccentric loading condition. So, I have considered both inclined loading as well as eccentric loading. So, last class I was discussing that we have to keep the loading within the middle one third portion of the footing. So, that there should not be any tension developed in the base of the foundation. So, I have selected this problem, that a rectangular footing of size 3 meter cross 6 meter is resting on a C5 soil with a depth of foundation is 1 meter. The water table is at grave depth, that means we have not considering the water table effect. The unit weight of the soil is 18 kilonewton per meter cube, and 4000 kilonewton load is acting on the footing with an angle 15 degree with vertical and eccentric in the direction of the width by 15 centimeter. So, that means if we draw the section, so that means if this is the footing, so if it is vertical, so it is acting, this load P is equal to 4000 kilonewton and which is acting at angle alpha is equal to 15 degree. And so, and if we draw the plan of the footing, so this is the center line of the footing and it is eccentric with so it is in center. So, that means the load will be eccentric. So, that is why I have to just correct this one. So, that means it is alpha value is this one. So, and so that means it is this is the amount of eccentricity. So, and this eccentricity E x is equal to 15 centimeter. Okay. So, and the vertical lengthwise direction there is no eccentricity. So, eccentricity is only in the widthward direction. So, it is widthwise direction is 15 centimeter and so that means the total width is B is equal to 3 meter. So, if I do that B by 6, so that is greater than 15 centimeter. So, it is within that curve portion. So, there will be no tension developed in the foundation. So, another one is that we can write that B dash is equal to B by 2 E x and L dash will be equal to L, as there is no eccentricity in the lengthwise direction. So, if there is eccentricity in the lengthwise direction, then we have to take the effective length also. So, that means the effective area will be B dash into L. In this case, if there is a two-way eccentricity, then it will be B dash into L dash. So, so now I am using the available theories. So, I have discussed about total 6 theories. First the Terzaghi theory, then the Skempton, then Meyerhof, then Henson, Basic and IS code. So, among these 6 theories, so I am because the Skempton theory is only applicable for phi equal to 0 condition, but here it is phi is there. So, we cannot use that theory here, and as well as Skempton theory, the eccentric incline loading condition is not incorporated. So, we are not using that theory. In the Terzaghi also, that incline loading theory is not incorporated. So, incline loading effect is not incorporated in that theory. So, that is why we are not using Terzaghi also here. So, remaining 4 theories we are using here, and let us see how we can use the different theories under this eccentric and the incline loading condition. So, first theory that we have considered, the Meyerhoff's theory, where we are using the net ultimate. So, this is the expression of the Meyerhoff theory. So, SC, DC, IC, I mean S, D, I are the shape factor, depth factor and inclination factor. So, here if the I is, I mean incline alpha is not, I mean loading is not inclined, alpha is equal to 0, that means perfectly vertical, then this IC, IQ, I gamma we have to not, we will not consider, because these are 1, because that effect is not there. But so here first we have to determine the NC, NQ, N gamma. So, that is why from the table, so it is 20 degree. So, NC is 14.8, NQ is 6.4 and N gamma is 2.9. So, that is why 14.8, 6.4 and 2.9. As I mentioned earlier also, that if the phi value that is given in the table is within that range, suppose the phi value is given 20 and for 25 or for 30 and your phi value is 22 degree, then you have to linearly interpolate that value between the given values. And so, now the Ex value is given 15 centimeter, that is 0.15. So, effective width will be 2.7 meter. So, effective width will be 2.7 meter and L will be as well as this is the, because there is no eccentricity. So, L will be 6 meter. Okay. And another thing, that here the eccentricity directly is mentioned, but sometimes the moment and the vertical load is mentioned. So, in that case, if the moment is in the lengthwise direction or the widthwise direction, depending upon which direction the moment is. So, suppose if the moment is in the widthwise direction, then we have to calculate the eccentricity Ex by m into divided by p. Okay. So, this p is that vertical load that is acting. So, these also eccentricity can be given, but here eccentricity is directly given. So, that is why we will have B dash and L, and when if I look at this so, these are the table for Meyerhoff bearing capacity factor. This is the table and this is for the 45 and 50 degrees. This is the table, the same table, and then these are the shape and the depth factor for Meyerhoff's bearing capacity equation. So, here the shape factor SC we are using. So, 1 plus 0.2 Kp B by L, and this is for any phi. So, as we are using it is for eccentric loading, and so that means instead of B we will use here B dash, and as L dash is equal to L. So, we will keep L. If there is the L dash also, so then you have to use B dash and L dash both. So, similarly Kp value we will get from this expression, this is tan square 45 plus phi by 2, and similarly for phi greater than 10, this is the SQ and S gamma factor, and similarly depth factor also we are using DC and DQ and D gamma. Okay. So, this is 10 greater than 10 degrees. So, we are using these expression, these two, and here also this will be B dash, this will be B dash. Okay. So, similarly, when now if I go back to the SC. So, SC this expression, this will be B dash L. So, if I put this value I will get 1.18. Similarly, SQ S gamma will give you 1.09. Now, DC will give you, this is dF by B dash. So, it is 2.7 because B dash is 2.7. So, it is 1.1 and this value is 1.09, and we have from this table that this is the IC, IQ, I gamma expression for any phi ICIQ, and this is was phi equal to 0 degree, and this is phi greater than 0 degree, this is phi equal to 0 degree. But I will use this one as the phi value is greater than 0 degree. So, this is the alpha which is 15. So, alpha value is 15 degree. So, if I use these factors, then I can get, this is the ICIQ 0.69 and I gamma is 0.06. So, ultimately if I put this value in this expression, so I will get the value of ultimate load carrying capacity is 740.55 kilonewton per meter square. Now, if I want to calculate the total load, then the Q will be A dash into Q net ultimate. Okay. Now, if I want to apply the calculate the safe load, then this will be A dash Q net ultimate divided by factor of safety, which is 2.5 to 3. So, this is the Meharov approach by which we are getting this value. Now, what I will do? I will go for the next approach, which is the Henson's theory. The basic theory is same, only the corrections factor, only the bearing these factors and the bearing capacity factors and these shape factor, depth factor, inclination factor, they are different. So, here the again that we have a table for Hansen bearing capacity factor, because NQ, because other values NC and N gamma, that we have to use the Meharov NC and N gamma in case of Hansen. So, that is why only NQ table is given, NC N gamma we have to take it from the Meharov's table. And so, that is why NC NQ are same, only N gamma is 2.9, as for 20 degree it is 2.9. So, that value is taken here, and again E max is 0.15. So, effective we did 2.7 meter, and then if we go for this factor. So, this is the factor. So, if you see this factor SC is equal to, if phi not equal to 0, this is the SC factor, which is function of NQ by NC B by L. So, here also instead of B we have to use B dash and L dash, because L dash is here equal to L. So, you will use the B dash by L. If there is a both way, then you have to go for B dash and L dash. So, now similarly here also B dash L dash, but this expression we will not use, because this is for phi equal to 0. So, I will use these expression, and for the SQ and S gamma I will use this expression, where this will be the phi dash B dash, this will be the B dash, and remember that these factor cannot be this is greater than 0.06. So, that cannot be less than 0.6. Okay, remember that if it is coming less than 0.6, then you have to take 0.6. Okay. And but when we are determining the DC and DQ and D gamma, so as per the Henson's suggestion, we will use B. Remember that we will not use B dash. Okay. So, because the idea is that because this effective area, so that will mainly affect the shape factor. So, that is why for the depth factor it is not used. So, this is the difference between Meharov, because Meharov we are using all B dash L dash, or whether it is shape factor or depth factor. But here in the shape factor we are using B dash L dash, but depth factor we are using B. Okay. So, this is the DC. So, as dF by B less than 1 in this case. So, we will use this expression, and then we will use this expression, and D gamma is always 1 for phi, for all phi. So, now if I go for this one, and then I will get this is the B dash. So, SC value, this is also the B dash. So, SC and SQ and S gamma value if I put in this expression. So, it is greater than 0.6. So, we have to use 0.82. Okay. So, similarly DC we have used the B, we have not used the B dash. So, and then DQ also we have used B, and then D gamma is always 1. Now, in case of Henson's approach, the inclination factors when I am calculating, which is there, we have to use the horizontal and vertical component of the load, because load is inclined. So, here H is the horizontal component and V is the vertical component, and there is a term C A, which is adhesion. So, as I mentioned that C A adhesion is always alpha into C. Okay. So, here C value is given 50 kilonewton per meter square, and alpha value we have to choose from this range 0.6 to 1. So, I have taken alpha value is 0.7 from this range. Okay. But in the assignment problems, so this alpha value may be given. So, you have to use that alpha value. So, that means this is the vertical component, and remember that, and this is the horizontal component. Another one, that here we have to use the effective area. Again here also that effective area we have to use, that is A dash. Okay. So, that means here inclination factor we are using the effective dimension, depth factor we are using the effective dimension, safe factor we are using the effective dimension, but depth factor we are not using the effective dimension, we are using the original dimension in case of Henson approach. But in Meyer approach, all the three factors, shape factor, depth factor and inclination factor, though in the inclination factor there were no dimension B or L, that means in safe and depth both factor we are using the effective dimension. So, this is the difference, that is why I am solving with different approach. So, now here if I use both, so this is not equal to phi. So, I will use this SC, and so I will use this one and this one, these three, because it is for these two are for any phi, and this is for phi equal to 0, and this is for phi equal to 0, and this one phi not equal to 0. So, now if I use these expressions. So, here the, as I mentioned that the vertical component will be P cos alpha. So, that means 4000 into cos 15 degree. So, this value is 3864 kilonewton vertical load, and horizontal load is P sin alpha. So, that is equal to, that value is equal to 1035 kilonewton. So, now if I put here, so it will be the effective area means 2.7 into 6. So, if I put this value, it will be 0.61, then IC is 0.54 and I gamma is 0.49. And then if I put this value here in this general expression, so ultimately this is coming out to be 639.51. Okay. So, now I will go for the next approach or next theory, that is our Weissig's theory. Again the basic equation is same. So, and but we have to use different bearing capacity factor. So, again here n gamma value is given, because the other NC and NQ will be same as the Meyerhof bearing capacity factor. So, we are using the same Meyerhof bearing capacity factor for NC and NQ, but n gamma Weissig has suggested a new factor, and that is the table, that is for the bearing capacity factor NQ only, because NC and n gamma we have to take for the Meyerhof table. And then for the shape factor and depth factor, which is similar to the Henson, but there is some difference. What is that difference? Because again this is a similar to the Meyerhof, to the Henson, but this one is I think this one is different, because in case of Henson it was sin phi, what I so in case of Henson it was, yeah, it was sin phi. Okay. But here it is tan phi. So, that is the only difference in this chart, otherwise all are same. So, yeah, otherwise all are same. Okay. So, only it is given A k, but that is also df by b. So, this is the shape factor for basics bearing capacity equation. But the difference is that in case of Henson's, we use effective dimension for shape factor, but we did not use the effective dimension for the depth factor. But here shape factor and both depth factor, we will not use the effective dimension. The recommendation is that we have to use both cases the actual dimension, that means B and L. Okay. So, that is the major difference between this when it is incline loading, because incline loading case only this effective area concept will come, otherwise that means you have to use the B I L, but in the Henson in shape factor you have to use the effective dimension, and but in case of basic in shape factor also we will use that the actual dimension which is B and L. So, now and for the inclination factor which is also similar, but here in case of Henson it was 5 to the power 5, but here it is to the power m. So, how I will calculate this m? So, m we can calculate by using this expression when h is parallel to b. So, in our case, this case h is parallel to b. So, we will use this expression, but if your eccentricity is in lengthwise direction, in that case h will be parallel to your L. So, if because here if this is the width, so if your width is if this is the width, so your load is acting in this way. So, it is parallel, this h horizontal component, this is the vertical component. So, horizontal component parallel to the width axis. Now, if your horizontal component is parallel to the length axis, this is V h in that case, because this is L in that h axis, then you have to use these expression. But remember that when I will calculate m, we have to use the actual dimension of the footing, that means B and L, but we have to use effective area when we will calculate the inclination. So, that is why I am explaining this portion in detail, because there are where you have to use which dimension. So, that is important. So, in basic all the factors you use that actual dimension B and L even for m calculation, but when you use this area for the inclination, so then that case you have to use the effective area, that is the recommendation. So, and that is why if I use these values, so similar way I am using, that is why B by L for SC, SQ and S gamma, and because it is also greater than 0.6, so we will take 0.8, and DC also I am using the B and DQ also, and when I am calculating M, it is in width direction. So, and using this actual dimension B by L, but here I am using the effective area 2.7 cross 6. So, ultimately I will get this coefficient and M value is coming out to be 1.67. So, if I put this expression, so I will get 0.57, and if I remember that if in the original expression that will be B dash. Okay. So, that is true for all the cases. When I use the B dash, so that is true for all the cases, but when I calculate the calculate the factor correction factors, in those cases we have to use different dimension in different cases, and ultimately this value is coming out to be 800 kilonewton per meter square. So, next approach I am considering that this is basic bearing capacity factors and the correction factors. And next approach, the IS code method. The IS code method here, in IS code method we have to use as per IS code method. So, here also I have used the actual dimension by actual equation, but IS code method suggests that in here also, because this is n q n dash, this one, this is actually this term is n q minus 1. So, this is not there as per the IS code, but this is a general expression. So, in the IS code you use this one, but then your value will be slightly changed, because if I use, because this is the actual recommendation for n q minus 1 as per IS code, but other case you have to, as I mentioned, you have to follow these general expression, but as IS code is recommended n q minus 1. So, we will use that n q minus 1. So, about this IS code, the n c n q n gamma is the basic n q n c n gamma. So, that means we will take the n c n q from Meyerhof's table and the n gamma from basics table, and then we will use the effective. So, this is the all the cases I have to use the effective dimension. It is for shape factor and for depth factor and for inclination factor. So, this is the table. So, all the cases you have to use the effective dimension. This will be the b dash, this will be L dash, B dash, L dash, B dash, L dash, okay. And here also it will be B dash, B dash, B dash, depending upon the which one you will consider, it is mentioned here. And this is the alpha is 15 degrees. So, depending upon the your condition, you will choose the appropriate factor. And so, now if I put these values, so remember that this will slightly change in this case. So, here this will not be here. So, in that case, in place of that, this will be the this is 6.4. So, it will be this one will be 6.4 minus 1. So, this value will slightly change. Okay. So, just correct these things, it value will be slightly change. So, so because that is the way it is been represented. So, and then after I putting all these values, so I will get close to this value. So, now if I take all the values in one table, so this is IS code factors. Okay. So, now if I take all the tables, so Meyerhof is given 740.55 and Henson is given 639.51, basic is given 800 kilonewton per meter square, IS code is given 692 kilonewton per meter square. So, now if I use the actual IS code recommendation, this value will slightly reduce. Okay. So, this value will slightly reduce. So, or it may increase. So, what is the, so but that is the slight variation, but it will be around this one. So, from here I can see that Henson expression is given the lowest values, okay, but that also depend on the C phi value that you are choosing. It is not that always the Henson expression will give you the lowest value. So, that also depend the C phi that you are choosing. So, and then but this is the summary of this problem. So, I have used all this expression, and then after all the we have to calculate the factor of safety against bearing. So, the factor of safety only vertical component, against vertical component you will check. So, the actual load will be the A dash q net ultimate divided by the V, that is the vertical load is coming. So, if I use that, this is the effective area. So, and the factor of safety is coming 2.68, which is greater than 2.5. So, okay. But there is another term, the sliding. Sliding means there is a horizontal component. So, this horizontal component will slide the foundation, okay, in lateral direction. Okay. So, that also we have to prevent. So, how we will check that? So, simple that we have to use that our C A into the effective area over which it is acting plus the normal force into the tan delta. Tan delta is the friction between any other material to the soil. Here material is the foundation, maybe the concrete. Okay. So, that is why V value is taken here, delta value is taken 0.8 times of phi in this case, but in the problem it will be mentioned. So, here it is taken 0.8 phi and alpha is taken as usual 0.7. So, now if I put this value 0.7 into 50 divided by the horizontal component, because this horizontal component is only giving the sliding. So, it is 1.62 and the sliding factor of safety is 1.5. So, it is safe. So, this way we have to do the design, and remember that I have explained what are the difference when we calculate the different factors for different different approaches, and then whether in which factor you will use effective and which one you will use the actual dimension, that I have discussed, because it is different for different approaches. Okay. So, and the final one, that when I will now this is the bearing check is done, I have to do the settlement check. So, in the settlement check you have to calculate that your Q A not net pressure, that is that the pressure that will be the vertical component and the effective area, that will be your net pressure which is acting, the vertical component of the Q n, and when you calculate the settlement. So, then in that case, so in your settlement calculation you consider B equal to B dash, and your net stress that is acting on the base will be the vertical component of your load divided by net area. So, that will be the net stress acting at the base, and you consider that, and instead of B you consider B dash, then rest of the calculations are same as I discussed for other problems for settlement calculation, whether it is in sand or it is in clay. Okay. So, now just one thing. So, in the lecture 13 I have solved the same problem with a value of phi equal to 40 degree and C was 0. Now, I have taken a sets of different values of C and phi, and let us see what is the difference of different theories. I have now here I have taken your C is equal to 50 kPa, phi equal to 20 degree, and previously lecture 13 I solved the similar problem with phi equal to 40 degree and C equal to 0. Okay. And in the next problem I will solve with phi equal to 0 and C with some value, and then we will compare make a table and we will compare what is the difference between the all the theories. Okay. So, the bearing capacity expressions is same for this is, but this case I can use the Terzaghi, and if it is pure clay then I can use the Skempton also. So, you can use the Terzaghi, the expression is same, and I have discussed the how I got this correction factors, and this is the NC, NQ, N gamma, and this is the correction factors for the rectangular footing. Similarly, this is the Terzaghi bearing capacity factor table, where I am getting that value, that 20 degree is 17.7 and 7.5 and 5. So, that is the value I am taking. And so, then for the Meyer-Hoff theory, the same theory I am using here, and for this I have explained how I am using these factors from the table, and then I am getting this value. Similarly, for Hansen theory I am getting 1204.7, and then I am using the Vesics theory, where this is not the inclined or eccentric load, this is the same problem with vertical loading. So, that is why all dimension are the actual dimension B and L, and then there is no eccentricity no inclination. So, that inclination factors are also not calculated, because inclination is not there. And then this is the other values, and this is the IS code, where this is here the actual condition is taken, and then this is the IS code, and the same problem I am solving with C is equal to 100 kPa and phi is equal to 0. Okay. So, our phi is equal to 0 degree and Cu is equal to this, that means this will be the Cu is 100 kPa. So, now I can use the all 6 theories, because it is only for the clay. So, I can use it for the Skempton also. Okay. So, now if this is the Tarzaki's theory, then this is the Meyerhoff's theory I am using, and with these all factors, again the load is perfectly vertical and acting at the center, that means no inclination, no eccentricity. So, and this is the value, and similarly for Henson's theory I am getting this value. Okay. And for using the Vesich's theory I am using 633.09 kilonewton per meter square. If I use the IS code method, then I am getting 633.09 kilonewton per meter square. Now, as I mentioned, I can use the Skempton theory also. This is for the rectangular footing. So, this is the Skempton theory. If I put this value dF by B, and this is the net ultimate C N C or C U N C, and this is the value that is coming out. And so, now I have taken all the combinations. This is for phi equal to 0, Cu equal to 100 kPa. This is phi equal to 20 degree, C equal to 50. This is from the lecture 15. This is lecture 15. Okay. So, this is lecture 15. I am taking the phi equal to 40 degree and C equal to 0 degrees. So, these are the all values. So, from here you can see for only cohesive soil, this Skempton is giving the lowest one. These all the three values are same, okay, for all these three methods, and Meyerhoff is given slightly lower values. Okay. From these 5, and this is the lowest, and from this one is all the theories are given more or less the same values, and here Meyerhoff is given slightly higher values, and Tarzaki's bearing capacity theory is giving values within the, I mean it is in the almost the average value is given. So, but it is not the all the cases. So, that is why my intention to do all this problem in different shear parameters is that depending upon your C phi strength parameter, your different theory, it does not mean that one theory always will give you the higher value, one theory always give you the lower value. It is not like that. It may change depending upon the strength parameter values that we are considering. So, now as I mentioned for cohesive soil, that Hansen theories give better prediction compared to the Tarzaki's theory, but here I have used Skempton for all the problems on clay, because it is giving the lowest value. So, to be in the safer side I am using that, but here now the question is which equation we will use. So, as you can see that Tarzaki's expression is simple one, and you can use it because it is given the average value, and it is also given almost the similar type of value for other theories. It is given within the middle of the all the range that I have received. So, that is why I can use the Tarzaki's theory, because that is the simple, but if the loading is inclined, then that we can use for the Meyerhoff's theory, because that is also predicting values which is slightly lower side. So, that is why depending upon that which theories you are using, so that you have to decide, but this is the as an engineer you have to decide which theory you will use, because ultimately that is the table I have shown you, that it does not mean that one table will always give you the higher value, but I would recommend that for the soft soil only clay Skempton is a good one, and for other theory you can use the Tarzaki, because it is giving because it is very simple and it is given more or less reasonable value, and but if it is incline loading, then you can use the other theory is like Meyerhoff theories, And so that's why this is the comparison of the all the theories. And so this is the end of the shallow foundation part. So next class I will start the next chapter, which is the deep foundation and mainly the pile foundation, and I will discuss the pile foundation under compressive load only. Thank you.